Okay, so good. So I think a couple of you have already looked at that exercise, and I think Chaitanya has sent his corrected result, the CV squared and CA squared. But I still don't understand what it has to do with helicity per se, helicity suppression that we talked about. Why, if you have CV equals CA, to be anything? I mean, of course, we want the sum of CV squared and CA squared to be 1. How they distribute themselves and why does it lead to, this dependence? It's not clear to me. I think it has more to do with the masslessness of the neutrino than actually the V minus A structure. So that is the only resolution that I have, which is probably along the lines that you also saw. Okay, so I think we wrote down, or rather we were going to write down the expression for for the width. So let's see here. Here's a pion which comes in, and then there is a W emission, and then there is an L and a new L like that. And then this was a W, and then this had a momentum P, and then this had a momentum P3 and P4, according to one of the books that I was using. And the matrix element was written as GW squared by 8 MWC squared. We have to start getting used to this, either writing it in terms of the Fermi constant or in terms of GW and MW. You have to get used to all these different things. When we talk about standard model, it means that every one of these parameters are things that you have to be used to. So then we wrote this down as U bar 3 gamma mu. Then we later decided to write this as CV minus CA gamma 5 V2. Oh, this is V2 and 3 like this, and F mu. And we said F mu is F pi times P mu. And if you do the full calculation, which is given Griffiths, and I urge you to do this, do all the kinematics, do the phase space. Here is a case where you don't have to do any phase space integral because it's a two body decay, so energy momentum conservation just fixes the phase space for you. Okay, and the two body kinematics also we have done earlier. And then the width, the expression for the width with this definition is given by F pi squared by pi h bar m pi cubed and GW by 4 MW to the 4th power ML squared times m pi squared minus ML squared. Okay. So the ratio, or the branching ratio, essentially this thing is dominated by muon. It's almost 100%, but it's still important to have these two things separately. And this is what this Penn experiment does. One of you is supposed to be doing the Penn experiment, which is pi to E nu experiment. So this is pi minus goes to mu minus plus mu bar like this. So this then would be me squared times m pi squared minus me squared divided by m mu squared times m pi squared minus mu squared. Okay, please put in the numbers and tell me what this number is. Okay, quickly, let us do this. Everybody take out your calculators or Mathematica and just work out this number. And now I'm not going to tell you these numbers anymore. You have to know what these numbers are. M pi squared minus me squared, m pi squared minus mu squared. It's just this expression, the ratio of these two. Okay, but there's also another underlying hypothesis over here, which is that of lepton universality. We are saying that the coupling constants are the same irrespective of what the lepton is. Okay, the rest of the physics is sitting in the actual masses of the particles, but we are saying that the coupling constants are all the same. Okay, so underlying this expression is the assumption of lepton universality. So this is, of course, it's a feature of the standard model, But in principle, we can also test this experimentally. Is this really true or not? Okay. So an experiment like this pen experiment is supposed to do these things. Okay. Yeah. So somebody work this out and tell me what the answer is. You can also have a radiative decay where there is a, a photon is emitted from the external charged, or you can also have initial state radiation or a final state radiation. Well, initial state won't count, but definitely in the final state, you can have a photon that attaches itself to this charged lepton, and then you can have something like a Bremsstrahlung correction to this also, but that'll be down by a factor of alpha. Okay. Anybody? Number? That's not what I get. What are the numbers you put in? Okay, that's too small. We can throw it away. Mu. Yes. Yeah. So here, this also has a correction, no? Yeah. Is that what you get? I see. No, it's a ratio, no? So this is just a pure number. Yeah. 511 and what units are you taking it in? No, that's yeah, okay, good. Yeah. Okay, so you people can, I somehow wrote down a much smaller number. No. Okay. What did you get? Okay, that may be correct. Okay, because I have somehow written down a wrong number. Okay, fine, very good. So this you say is 5.5 5.4. Let's times 10 to the minus 5. Okay, so that is what you also have. Very good. Okay, but now I want you to calculate this also. But I have to tell you what this F pi is. This F pi is equal to square root of 2 times 92 MeV times 0.97. What are the different factors over here? So there is a different convention. Different books have different conventions for this F pi. Okay. So Griffiths has a habit of often not saying what is the value that he is using. So I had to compare with other references, and then I figured out that this F pi is square root of 2 times the standard value of 92 MeV. And what is this? This you have to tell me what this is. All of you by now you should know what is 0.97. This is the cosine of the Cabibbo angle. You see here there is a cosine of the Cabibbo angle where the W. See here we said this is universal. We said that the lepton coupling is universal, right? But the quark coupling is not universal. It depends on what are the flavors of the quarks. It's multiplied by a factor which is elements of the CKM matrix. Okay, where C stands for Cabibbo, which is in the 2 flavor approximation, and the cosine of theta C is 0.97. Okay. Okay, cosine of theta C. Okay, now people just work this out and tell me what is the answer that you get for mu, for L equals mu. Okay. By now you all know what is GW. GW is 0.653. MW is 80.4, no? GeV, please note. And we know the rest of these things, and let's put this in. And then at the end of this, let us look at what is the dimensions of this. MeV squared, wait a minute, this I think also has a square over here. Ah, now I know. There's a square over here and a square over here. So this answer is wrong. It should have been. Now you can quickly check this in your Mathematica program. I forgot this power of 2, and you tell me what this is. Yeah, both of them. Yeah. Yeah, 1.3 times 10 to the minus 4. You see, you people have to keep an eye on, because I have this unfortunate habit of making all these mistakes. So you have to keep an eye on what it is that I am doing. Okay. Okay. 2 plus 4, 6, 8, 8, and down here we have 7. Okay. So this whole thing now has dimensions of GeV. So we have to divide it by h bar, and the value of h bar is 6.5 times 10 to the minus 25 GeV, right? GeV second. So then if you plug in these values, then you should be able to get the width in seconds to the minus 1. So let's see what you get. See, all these things are going to be in the spirit of a tutorial, okay? Not all the time, but a good part of the time what we will be doing in the standard model course is just tutorial type. Okay, good. Because without knowing these numbers, there's no point in doing all kinds of very complicated stuff. Did you get something? Hmm? Yeah, but are you sure you're putting everything in the right units? No, this was in MEV here. Okay, so let me 10 to the minus 3 GeV. Okay. Okay, so yours everything is in MEV. What about the W?
W I put a 10 to the 3 to put it.
Okay, very good.
So, and same with h bar 10 to the minus 3.
Yes, very good. Okay.
Let's to, maybe I can.
F pi squared.
10 power minus 22 or 10 power minus. I have to say GeV is in the
No, 22 is right.
the numerator, so you have to multiply by. So this should be what 1, 2, 3, 4, 2 times 10 to the minus 4.
I still don't get it. Okay, m pi cubed.
I forgot the square here.
Again, that's my fault. Did you have the m pi cubed downstairs?
M pi cube.
Okay. F pi squared divided by pi h bar m pi cubed GW divided by 4 MW to the 4th power ML squared m pi squared minus ML squared squared. So F pi. Okay. Yeah. Yeah. Yeah.
This is 80.2.
Yeah.
Also an MEV.
Yeah. No, but why did you take to the power of minus 1? Don't take the minus 1.
So you want the width?
Yeah, for the moment the width. Okay. So that I know how to check it. Yeah, 3.7 times 10 to the 7 second inverse. Okay. So the lifetime then is, so this, what did you say this was now? So this is equal to 3.7 times 10 to the 7 second inverse, and tau therefore is inverse. (2.7 times 10 to the minus 8 seconds), right? So this is the lifetime of the pion. And what is the basic scale that we already discussed the other day? It's microsecond is the lifetime of the muon. Okay, it was 2 times 10 to the minus 6 seconds. So this is 2 orders of magnitude down compared to the lifetime of the muon. Okay, so these are the numbers that you have to remember. And you will remember what the pi 0 lifetime was. You remember what's the pi 0 lifetime? Pi 0 to 2 gamma. Gamma was 7.75 eV. So let's compute the this in seconds. So what do we have to do now? 7.75 eV divided by where is my h bar? Here. So 6.5 times 10 to the minus 16 eV second. Okay, can you tell me what this is? This must be something like 1.2 times 10 to the 1.2 times 10 to the 16 second minus 1. So the lifetime of the pi 0 is the inverse of this. So let's get what that is. It's about 8 times 10 to the minus 17 seconds. Is this right? Just check this. It's okay? Yeah. Now you see here, even though the pi plus and the pi 0 are cousins, they are all members of the isospin triplet. But you see how many orders of magnitude there is difference in the lifetime between the two. There is 9 orders of magnitude. The pi 0 is extremely short-lived. Okay, but this is very useful. Why is it very useful? Tell me. A pi 0 that decays in its rest frame, what is it going to produce? 2 photons, right? Which are back to back. Okay, so if you have a detector which sees 2 correlated pions of the same energy, you know, it has to be the same energy from energy momentum conservation, then your detector can say definitely that it was a pi naught, right? Even if the pi 0 is boosted in the laboratory frame, let's say that it's going fast, then in the rest frame it's going to produce 2 photons back to back, and both of them are boosted in the laboratory. So you'll have 2 photons coming out, and in the detector, if you see 2 photons, essentially you can track them back and you can see where the parent pi 0 was. Okay, so that is why pi 0 is a particle that is easy to detect and easy to identify. If you go to an experimental talk, they'll say that we were able to identify the pi 0s because of the very nice decay that it has, which is pi 0. On the other hand, the pi plus is not a very nice decay. Why is it? Because the neutrino disappears and you're never going to see it. So you'll see only one particle. And from that particle, you have to infer there'll be missing energy which the neutrino carries away. You have to infer from the muon that you see that it came from a pi plus. Okay? Those are all backgrounds. See, for an experimentalist, they must have some confidence, no? Or then you have to apply some cuts on the energy of the photon and all these things and the directionality. So whenever you go to an experimental talk, you'll hear them talking about all these things, about their cuts, the acceptance of the detector and all these things. But I am merely talking about the signal over here. Okay, how to get rid of the background and then keeping only the signal. Okay, one more decay of the pi. Since we are spending so much time on pi's, why not spend even more on the pi? So this experiment, I don't know which one of you is going to do the low energy experiment. So this PEN experiment and this pi beta experiment are the guys who have carried out these measurements at high precision in the recent past. All these things have been known for a long time, but it's a matter of the precision now. Okay, so you can also compare this with an expression in the famous book of Donahue, Godovich and Holstein. They also give. They tell you exactly what is the F pi they're using and all, which good old Griffiths doesn't do. Okay. So here let me say a few words about pion beta decay. And this is from the same book, the Scheck's book. So what is the quark diagram that we have over here in order to get this thing? So here, let's say, so let's say that this is a U quark and the D bar quark, and let's say that this is pi plus. So the pi plus is such that it emits a W and then produces a D quark, so that this now becomes a pi 0. Now pi 0 actually is 1 by root 2 times U bar minus DD bar, like that. But then roughly speaking, you can say that this is the quark level diagram from which, what can you have in the final state here? Now tell me, what can you have in the final state over here? You have to conserve the charge. Therefore, this must have been a W plus. So what can this be? Only one lepton, because the mass difference is rather small, right? Only the electron, or in this case positron, E plus and the nu, for instance, and of course the corresponding charge conjugate. So here the expression according to Sheck is g squared cosine squared theta 1, he calls it theta 1, the same Cabibbo angle, times delta to the 5th power divided by c pi cubed times 1 minus 3 by 2 delta by m, something known as k. This is the phase space integral function times f plus squared at 0, which is the corresponding form factor for here, and delta is the mass difference between the two. And what is the mass difference between the pi 1 and the pi 0? Mass difference 139, by now we all know. No, pi 0, pi plus and pi 0 mass difference. Yeah, correct. 4.6 MeV. And epsilon is me squared by delta squared. This function k of epsilon is approximated by 1 minus 5 epsilon like this, and f plus at 0, so this comes from theory, this is equal to square root of 2, which comes from the CVC hypothesis. See, many students and many people who don't have my kind of age and experience think standard model is very simple, everything is known. You just have to write down the Lagrangian, you have to say what are the parameters, everything is known about the standard model. What this shows is it's far from it, okay? The actual phenomena that the standard model describes are extremely complicated. Nevertheless, even though they are so complicated, we are still able to make sense out of these things, okay? And the reason why we are able to make sense is, first of all, this kind of decay where you have the pi decaying, etc., not just involves the weak interaction, it also involves the strong interaction, right? Because the quarks are sitting inside a hadron and they are decaying. Nevertheless, we are still able to make sense out of all this because the strong interactions have certain symmetries, and we can use all those symmetries, etc., relate various processes, and then get information that we can use to actually, make sensible calculations. Yes.
So W minus and W plus are the same mass. Then why don't we have a big plus and big pi?
You tell me.
You said that pi naught is heavier, so that's
No, pi naught is 135 MeV, pi plus is 139 MeV. Okay, so the mass difference is 4.6.
not enough to produce.
Exactly. Yeah, exactly.
Having this mu plus from this W minus W plus or W minus.
That's W minus is there virtual. Yeah. So this is a way of writing it. It's actually a Fermi contact interaction which is actually doing it. It's a 6 fermion. But today we know that, look, there's a virtual W. Okay, so that W is not produced on shell. So the W is actually sitting over here in GW squared divided by 4MW. Okay, so now please calculate the width due to this, and let's get the branching ratio, and let us try to compare it with what we have. Yeah, let's put in the numbers and see what we can get. Actually, I want you to get this ratio, ratio of pi minus, let's say, going to pi 0 e minus mu e bar divided by gamma of pi goes to mu nu mu. This is the thing. With this, virtually the entire decay goes through this. So let's get this ratio. This we already had earlier. What was the number we had for this one? Yeah. Let me see. I have to turn this back. 3.7 times 10 to the 7 second minus 1. Let's calculate this and see what we get. G, what is capital G? 1.16 times 10 to the minus 5 GeV to the minus 2 squared, 0.97 squared. So this delta to the 5, now again this thing is in MeV, so we have to get 4.6 times 10 to the minus 3 to the 5th power. Now remember that we saw this 5th power somewhere else. Where did we see this 5th power? In the muon decay. Remember, it goes as mu to the 5th power. Whereas here, it's not the mass, but it's the energy. There in the muon case, remember that the muon is so heavy compared to the electron and neutrinos, the entire energy is available in the mass. Whereas here, there's practically no energy available, very small amount, and yet it's the 5th power of the energy. Okay, divided by c pi cubed times 1 minus 3 by 2 times, so this must be ME. So delta here is 4.6 times 10 to the, no, 4.6 divided by 0.511. Both are in MeV. So I'm all right with that. And then this ratio here, can somebody tell me what is this ratio? 0.511 by 4.6 squared. So this is roughly 1 by 10, isn't it? So this is about 1 by 100. How much is it? 1.1. Okay. Yeah. Yeah. It's about 1%. Okay. So let's see here. So that is 1 minus 5 times epsilon times 2. Okay. So this is what we want. And compute this for me, please. You get something?
For the ratio seems a bit small.
No, that's too small. Okay. So let's have a look. G.
I need to put yeah,
No, wait. No, G, that's in GV only. GV to the minus 2, in fact.
really to the minus two, so
Minus 3. You want everything in GeV or everything in MEV?
The G is
Yeah, so you leave the G as it is, capital G, okay. So, yeah, times 10 to the minus 3. Yeah. Mass of the electron also, mass of the electron.
this is the range.
Yeah, that's okay, mass of the electron.
It's just the ratio.
It doesn't matter, okay. Mass, that mass, 10 to the minus 3.
Oh, I'm not using it. Yeah. This number is what's this? The ratio that needs to be.
Yeah.
Okay.
Yeah. Yeah, what is the F? Yeah, square root of 2, okay. Yeah. Yeah. No, no, H bar you still don't have. Into the minus 25. 1 point, excellent. That's the correct answer. But what is the gamma? Let's remove the denominator, the 3.7, and let's see what we get. Why did you? No. You have still to keep 6.5. .4. That's it. 7 second minus 1. Okay, good. And this is equal to 1.04 times 10 to the minus 8. Now you see the reason for talking about this particular thing is it's a sensitive test of the standard model. Okay, it's a small number, very small, but still accessible to experiment. Not only that, it tests all the hypotheses of the standard model, including things like CVC hypothesis, etc. So once again, let me emphasize that the reason we are talking about these examples is you should not think standard model is just a theory of quarks and leptons and gluons and everything is known. No, especially when it comes to quarks, they are sitting inside hadronic matter or hadronic states. So everything that you say when you say standard model is checked and proved and demonstrated, it means that you understand the strong interactions without actually ever solving them. You have to solve them in certain sectors where it is possible to test properties of the standard model, of the strong interaction, Hamiltonian, all the symmetries, etc., such as in processes like this. I mean, you may want to say I'm going to build LHC and I'm going to build HL-LHC costing billions of dollars because according to you the standard model is all established. But it's established only when every one of these numbers is checked, right? So that's the reason for emphasizing all these low energy observables, so to speak. Okay. Yeah. Oh, thanks. Thank you. Like this? Wait, is it? Let me look at the book here. Delta by m is quite big. 3 by 2 delta by m. No, how can it be? 4.6 divided by O. There may be a typo, okay? But you got the right answer with this thing. No, but this 3 by 2, it says delta by m, but what is m over here? Wait a minute. It's m, it's not me, it is m. No, m is the mass of the pion, excuse me. This is the mass of the pion. Sorry. 139. What did you do? You still get the answer?
So that is the mass of the electron, not the pion. We still got
yeah.
That is alarming.
Yeah. No. It's just a very small number. That's why. You can just put it in and correct it. Let's see. Yeah. It's a good thing. Mass is a charged pion. Okay.
Will there be square?
No, there's no square. Thanks for keeping an eye on all my, all my slips, so to speak. So this is more or less the end of all the discussions of pion decay. I don't think we need to do much more. You can also have a corresponding thing for decays of kaons, where the d quark is replaced by the s quark. But the kaon is much heavier than the pion, so it has many other complicated decay modes also. And it's actually very interesting. It has enough energy to decay, as you know, into 2 pions and 3 pions and so on. And that is another of these settings where parity violation was actually discovered. The so-called theta tau puzzle, which was resolved by Yang and Lee, was to show how it is the same kaon which can decay both into 2 pions as well as 3 pions, because they were thinking how is this possible that a pseudo scalar like the kaon can decay either into 2 pions or into 3 pions. Sounds ridiculous, but it does. That's because kaon is a pseudo scalar, right? Decays into, let's say, 2 pions, each of which is a pseudo scalar, and then this parity is a multiplicative quantum number. So if you have 2 pions, then the final state will have a parity positive. So you may think that, hey, how is this even possible? It's because parity is not conserved in the weak interactions that such a thing can happen. So we are not going to get into that here to decay all these, to study kaon decays. But there's one thing that I had done earlier in the KK bar system, and please remind me what it was. What did we do with the KK bar system, and what did we prove or establish experimentally for the KK bar system, neutral KK bar system? You remember what we did, KK bar system? Yeah, so we showed that CP is violated. But there's one more symmetry, discrete symmetry associated with the special theory of relativity. C and P separately are violated by the weak interactions. CP is also violated by the weak interactions, but at a very small level. Is there one other symmetry that you know of which may be violated or conserved and so on? If CP is violated, what do you expect will happen? Is there any other symmetry that should be violated, you think? Yes. Not just time. Say the full word. Time. T stands for time. Time reversal. Okay. So time reversal in a reaction is what? Supposing you have n plus p. What can n plus p combine to give you? A neutron and a proton can combine to give you a, this we know, right? It's there in the oceans, right? Besides water, what is water? H2O, right? Which has 2 hydrogens and one oxygen. Okay. And what do we mean by hydrogen when we say hydrogen? The proton with electron going around. Okay. With atomic number 1 and atomic weight also 1. But that's not the only possibility. There's one more possibility with hydrogen. In fact, there are 2 more possibilities with hydrogen. What are those? Yeah. The chemical name is always fixed by the number of protons inside a nucleus. Okay, chemical name is fixed. So if it is hydrogen, it means that it definitely has only 1 proton and 1 electron, but it can have other things also in the nucleus. What can it have? Neutron. How many neutrons can it have? 1 or 2. And if it has 1, it's called a deuteron, and it's stable. We know that it's stable. Why? Because they're in the oceans, right? So as far as we know, somebody put it there at the time of the Big Bang, and it's still there, and it didn't decay into anything. Okay. And so if you took a neutron and a proton, as we did in the Big Bang, and then we just banged them all together, and then it formed this wonderful thing that's known as a deuteron, right? Deuteron. But then what does it do? Besides producing a deuteron, it can't just produce a deuteron, right? Because from energy momentum conservation, you can't collide 2 things. It has to produce some energy, which is the binding energy associated with the deuteron. What's the binding energy of the deuteron? 2.2 MeV or so. So the binding energy per nucleon is 1.1 MeV, 2.2 divided by 1. So these are the various numbers that you see in discussions, and you have to understand where it is coming from. And we know that the deuteron potential is very shallow, very deep like that, but the energy is very small. So the potential is very deep like that, and there's only one energy level. Does it have any excited states? Deuteron? Any excited states? Yeah. Yeah. How do we know that? Because if you try to excite it, it just disintegrates, right? So how do we know that this potential is very deep? Because in quantum mechanics, we always solve a problem, a toy problem of the Dirac delta function potential, and it's very deep. The delta function is very deep, but still it has one bound state. Only one bound state, okay? So this suggests that it's a very deep well, but it has only one energy and rather close to the continuum. Okay? So you try to do anything to this, it will break up. So it's a D plus gamma photon has to be produced, right? You know the. It's not because of the Coulomb. How is it possible? Only one of them is electrically charged, right? So it's not Coulomb potential. It's some very complicated interaction due to exchange of quarks and so on. But there are no quark degrees of freedom, pions, kaons, all these things. The internucleon forces are produced by the pions. Okay? So the effective potential, this is an effective potential. It's not an ab initio calculation of the potential or anything like that. This is the effective potential, which phenomenologically we know has to be rather deep, and then it has only one bound state. And then we also know that it's a mixture of S and D type and so on. Why? Because we know it has an octopole moment. All these things we know. So here is an example of a reaction. So if there was a time reversal invariance, then what is the kind of reaction that you would have, that you would predict? You would predict that it can also go this way, right? But what would you say about the rates for this direction and this direction? If time reversal is a good symmetry, they should be the same, and it has a name. What's the name? If you say detail balance, so you would say that these two are equal, and that's called detail balance. So you can say that time reversal implies an impulse like this. So this is okay because this is really the electromagnetic interaction. And we know that this should be okay also with strong interactions. Strong also is okay because CP violation implies time reversal violation. Okay. Why? Because we know that the full CPT theorem has to hold. And what did we say are the consequences of CPT theorem? Any of the mass of the pi plus? Yeah. Anything else? Let's say for this example, pi plus, pi minus, what can you say? I mentioned this to you. That's the trick question. It's only the total width that has to be the same. Total, not the individual. Total of pi plus, gamma, total. Or any particle and antiparticle. We can't really do this with weak interactions. Weak interactions, we cannot do any real experiments. No experiment is possible. Why? Because weak interactions, one may have to use quarks. Okay. But if there are quarks, they are always surrounded by the strong interactions, And you can't really do any experiments with that because the strong interactions will swamp out any of the weak interactions. Supposing it is with leptons and you want to do weak interactions phenomenology, you want to have a process and then you want to see the reverse process. You can't do it with neutrinos. I mean, it's impossible to observe. So it's almost impossible. Experiment is not possible. So the only way is to look at certain predictions of theory which would imply, you know, static properties for various particle states, which implies CP violation and T violation. So we have to look for properties of particles. So we can't do, not possible to do detailed balance. Possible to do detailed balance with reactions. So we have to look for properties predicted which violate CP, or T. And believe it or not, it's something very simple. It's the existence of permanent electric dipole moment. Permanent electric dipole moment of a fundamental particle, of an elementary particle. Please don't tell me that ammonia molecule and methane molecules and all have EDMs and therefore it's a signal of CP violation. It's not true, because those are quantum mechanical systems with degenerate energy levels. So we are not looking at examples like complicated things like methane or ammonia and things like that where it may have an EDM. We're talking about elementary particles. Elementary or basic particles like neutron. We know neutron is not elementary, it's composite, it's made up of quarks, but it's not like there are many degenerate states of the neutron or anything. It lives in its ground state, that's it. No excited states, no nearby states, and so on. So the measurements according to according to Griffiths, there must be new numbers now. This is now bounded from above by 6 times 10 to the minus 26 e centimeters. So whoever is looking at the low energy experiments is supposed to survey this particular quantity, and d of the electron is 1.6 times 10 to the minus 27 e centimeters. So these are the present bounds on these quantities. Since I mentioned all these properties, I also want to take a digression, because anyway you're all mature students and you learn all this on your own, so I may as well tell you some stories. Right or wrong? Right? This guy